Hello everyone, my name is Vyshali and today we will be discussing the module 4, which is the applications of quantum mechanics, starting off with particle confined in a 1D box. The particle in a box is a concept based on the Schrodinger's wave equation and it involves mainly three steps. First, we have to solve the time independent Schrodinger's equation to get the wave function formula. And then we have to show that energy levels are quantized using boundaries at both 0 and maximum L. And then we have to complete wave functions using normalization. So here we can see a box which is one dimensional and it can be placed anywhere between length 0 to L. And it is basically a square potential well with infinitely high potential barriers at each end. After solving, we get k square is equal to 2 me by h square, and the wave equation can be given as a sine kx plus b cos kx. Using the boundary conditions, we get b is equal to 0 when x is equal to 0 because even the wave function will be 0 and this gives kl is equal to n pi. Using this, we can derive further the allowed energy values of a particle, which is n square, pi square, h square by 2 ml square, while n is quantum numbers from 1, 2, and onwards. Energy levels are quantized and are not equispaced. The lowest allowed energy is greater than zero. Hence, we can say that the particle is never at rest. E1 is called the zero point energy, and En are called the corresponding eigenvalues. The corresponding wave functions can be given as a sine n pi x by L. On the left, we have the sketches of the wave function, and on the right, we have the probability density for quantum numbers 1, 2, and 3. Now we will move on to the nanophysics segment of this module, particularly learning about nanomaterials, which are defined as substances having size roughly 1 to 100 nanometers. They are not as small that they can't be seen, but they have a large surface or long wire whose thickness is in scale of nanometers. They can be used in thin films or surface coatings, and two-dimensional examples include nanowires and nanotubes, whereas three-dimensional examples include precipitates, colloids, and quantum dots. Nanoscience can be defined as the study of phenomena and manipulation of materials at the atomic, molecular, and macromolecular scales, where properties differ slightly from those at larger scale. So, what makes these nanomaterials different from other bulk materials which we see in our day to day lives? The properties of these nanomaterials are very different, primarily because of two factors. The first being increased relative surface area, and the second being quantum confinement effect. Most of the physical and chemical attributes of nanomaterials is due to the surface volume ratio, which is also defined as the surface divided by volume. Nanomaterials have a relatively larger surface area when compared to the same volume or mass of the material produced in a larger form. As the material size reduces, the S by V ratio increases. Nanoparticles have larger surface area. Hence, if the A by V is ratio is higher for a decreasing size, The reactivity increases because of more surface atoms. For example, if we have a sphere of, say, radius r, then the surface area will be 4 pi r square and the volume will be 4 by 3 pi r cube. The given volume is divided into smaller pieces, hence the surface area increases. As the particle size decreases, a greater proportion of atoms are found at the surface compared to those inside. Nanoparticles have a much greater surface area per given volume compared with other particles. And this is what makes these materials more chemically reactive. Nanoparticles have properties which are very unique and distinctly different from those of bulk materials. They are mainly crystalline in nature, and we will explore these unique properties. Physically, the crystal structure of nanoparticles is same as bulk structure with different lattice parameters. The interatomic spacing decreases with size, and this is due to long range electrostatic forces and the short range core repulsion. The melting point of nanoparticles also decreases with size. As for chemical properties, the electronic structure of nanoparticles is dependent on its size and the ability of nanoclusters to react, which again depends on the cluster size. The large surface area to volume ratio results in these nanoparticles having a strong effect on catalytic properties. They also have several electric properties in the domain of resistivity and conductivity. The density of the energy states in the conduction band changes. And when the energy spacing between two levels is more than kBt, an energy gap is created. If the material size is more, the band gap will be less. Nanoclusters of different sizes will have different electronic structures and different energy level separations. Hence, the ionization potential at nano sizes are higher than that for their bulk correspondence. The magnetic moment of nanoparticles is found to be very less when compared with their bulk size correspondence. The nanoparticles are made up of semiconducting materials such as germanium, silicon, and cadmium. Magnetic properties don't vary if we change size of a bulk material because number of magnetic domains doesn't change significantly. However, non-ferro bulk materials exhibit ferromagnetic-like behavior. As for other properties, we have optical properties such as absorption, transmission, reflection changing with size due to quantum confinement. And we also have mechanical properties like smaller size results in there being lesser imperfections in nanomaterials like dislocation and vacancies. Nanomaterials can be created by either physical or chemical methods. Physical method includes ball milling, sputtering, and evaporation, whereas chemical methods include electrodeposition, chemical reactions, and chemical vapor deposition. Nanomaterials are a boon and are used in several fields. For example, the chemical field, wherein they are used in fillers for point systems, coating systems based on nanocomposites, and magnetic fluids. In the automotive industry, they are used for lightweight construction, painting, catalysts, and sensors. In the medical field, they help in drug delivery systems, are used in active agents and medical rapid tests, as well as in antimicrobial agents and coatings. They are also agents in cancer therapy. In the industry, they help in data memory, displays, laser diodes, glass fibers, filters, and conductive coatings. They also act as energy sources, like in fuel cells, solar cells, batteries, and capacitors. They are even included in cosmetics, for example, in sun protection creams or toothpaste. Quantum confinement is a phenomenon in which if we reduce the size of a material from bulk size, electrons get confined to the region of size of the material. At these confinement length scales, the electronic energy levels are not continuous as in bulk, but instead are discrete because of confinement. Hence, quantum confinement is defined as the spatial confinement of electrons in one or more dimension. There are three types of quantum confinements. First is the quantum well, which is a 2D nanostructure in which there is confinement along one direction and the particle is free to move about the other two directions. Particles possess discrete energies associated with the confinement dimension. Particle energies are continuous along the other two unconfined dimensions. Examples of quantum wells include graphene, MOS2, and WS2. Next comes the quantum wire, which is a 1D nanostructure in which there is confinement along two directions and the particle is free to move in the third direction. Particles have discrete energies associated with these two directions of confinement and it is continuous along the third unconfined direction. Example of a quantum wire is carbon nanotube, gold nanowire, and GaN nanowire. The quantum dot is also known as the zero-T nanostructure. In this case, the number of degrees of freedom of the particle is zero. The particle has discrete energies associated with its motion along all three directions. Examples of these are nanoparticle clusters, colloids, gold nanoparticles, CDS, CDSE, CBS, and fullerenes. Now we will explore the phenomena of quantum tunneling, in which an object, such as an electron or atom, passes through a potential barrier, though it does not have sufficient energy to penetrate. In other words, quantum mechanics says that there is no region that is inaccessible to the particle, regardless of its energy. As seen in the diagram, in regions 1 and 3, the potential energy is zero. Hence, the particle's wave function can be described using the wave function for a free particle. However, in region 2, the total energy is lesser than the barrier height, which is denoted by U. As the wave incidence on the barriers from region 1, a part of it can get reflected and the rest is transmitted. Where in one hand classic mechanics says that there is one impenetrable barrier and it cannot be transmitted, quantum mechanics allows us to think in a different way, whereas it can both be reflected as well as transmitted through the tunneling effect. We can find out the potential, momentum, and the solution for k, which is equal to root under 2m e minus u by n. This diagram shows the bias dependence on tunneling. EV is the vacuum level or the reference energy level. EF is the Fermi level, which is the highest occupied level in a metal. The work function is defined as the amount of energy needed to remove an electron from the bulk to the vacuum level. If the sample bias is positive, the Fermi level of the sample is less than that of the tip. So electrons flow towards the sample. When the sample bias is negative, the Fermi level of the sample is at a higher level than that of the tip. So the electrons travel from the tip to the sample. We can also calculate the reflection coefficient and transmission coefficient in a tunneling effect. Refraction coefficient is denoted by R, which is B square by A square mod, and transmission coefficient is given by T, which is F square by A square mod. The overall tunneling probability is given by exponent of minus 2 K2 alpha, where alpha is root under 2m u minus e by h. The expression for the wave function at each region is given in the following. For the first, we have the coefficients as a and b, both positive. And in the second region, we have the coefficients as c and d, whereas in the third, which is the transmitted area, the coefficient is f. And we also see the boundary conditions both when it is x is equal to 0 and x is L. The transmission coefficient is also given by this similar formula, and we can also say that the transmission probability falls off exponentially with the barrier width. Lesser the barrier width, more is the transmission probability. These are the graphs for the density of electron states for different nanostructures, different levels of quantum confinement, such as 3D, 2D, 1D, and 0D. The scanning tunneling microscope was a groundbreaking invention which can sense the surface by using an extremely sharp conducting tip that can distinguish roughness smaller than 1 angstrom with zero point 0.1 angstrom depth. This allows for the imaging of the surfaces of metals and semiconductors at the atomic level. It was developed by Gerd Binnig and Heinrich Rohrer at the IBM Zurich Research Laboratory in 1982. Both of them almost received a Nobel Prize in Physics for developing the STM. The invention of STM led to the discovery of many others, like atomic force microscopy, scanning tunneling spectroscopy, magnetic force microscopy, and etc. This is the diagram of a stylus profiler made in the 1929, where you can see the mirror is used for reflecting the light source and the photographic film captures it. Below is a tip and a moving stage. This can generate profile images up to 1000 magnification. The topographiner, made by Young in 1921, consists of a X and Y piezo drivers which scan the tip over and slightly above the specimen value. The Z piezo is controlled by a servo system to maintain a constant voltage and hence a constant separation between the tip and the surface. An electron multiplier detects the tiny fraction of the current which is scattered by the specimen surface. The STM is based on the basic principle of the electrical interaction between two metallic electrodes. It consists of a sharp tip that is connected to cathode of the battery and the sample to the anode. When the tip is brought very near to the surface of the sample, electrons tunnel through the vacuum, separating the tip and the sample. The tunneling probability decreases as the tip to sample separation increases. We will discuss the construction of the scanning tunneling microscope. The metal tip permits electrons to tunnel between the tip and the sample. There's a piezoelectric scanner which helps in the fine tuning of the height. It can change its length depending on the voltage. The current amplifier makes sure that the tunneling current we get is amplified for proper detection, and the battery is used to apply voltage between the sample and metallic strip. The feedback loop is used in constant current mode. The tunneling current depends on the sample tip separation, as number of electrons that will actually tunnel vary depending upon the thickness of the barrier. The changes in surface height cause changes in the tunneling current. First, the tip is brought close to the sample. Second step, the bias voltage is applied between the sample and the tip. Then, the fine control of the tip position is achieved by piezoelectric scanner tubes whose length can be altered by a control voltage. The scanner is gradually elongated until the tip starts receiving the tunneling current, which ranges from 4 to 7 angstrom. Once the tunneling is established, the sample bias and the tip position with respect to the sample are varied according to the requirement of the experiment. The first mode of scanning is the constant height mode, in which the mode changes of the tunneling current, which is mapped directly. Next is the constant current mode. The voltage that controls the height of the tip is recorded, while the tunneling current is kept at a predetermined level. The STM tips might use cut platinum iridium wires or tungsten wires, which are chemically etched. Even tungsten sharpened with iron milling can be used, and the best tips have a point few hundred nanometers wide to provide proper range. As for vibration control, we can use coil spring suspension with magnetic damping and stack metal plates with dampers between them. We can control the tip accurately due to the help of piezoelectrics, and the displacement is accurate up to zero point 0.5 angstrom. As for interpreting STM images, the topography model is good for large scale images but not for the atomic level. Electron charge density models are more accurate for atomic level images. The best model requires complex quantum mechanical considerations. Here we have the example of the silicon reconstruction. These images vary depending on the electronic state of the material or the tip. STM has also helped us obtain images of graphite, wherein we can see the crystalline structure of graphite, and the overlay of the structure shows only every other atom which is imaged. Even a sophisticated machine like the STM is not without its merits and demerits. Advantages are that it does not cause any damage to the sample, and the vertical resolution is superior to the SEM. The spectroscopy of individual atoms is possible at a relatively low cost. However, the disadvantage is that the samples are limited to conductors and semiconductors, and it is generally a difficult technique to perform. The maximum vertical resolution is zero point 0.1 angstrom, and maximum lateral resolution is 1 angstrom, whereas the maximum field of view is 100 μm. Now, where can this STM be applied in real life? It can be used to compare bulk structures, and it can also be used to create semiconductor surface structures, nanotechnology, and superconductors. They are used in metal catalyzed reactions and spectroscopy of single atoms. They can also help in future developments, like improve the understanding of how electronic structures affect tunneling current. And this is the development that STM offshoots. It is used in catalytic processes wherein the tunneling current can be used to dissociate single O2 molecules on platinum surfaces. After dissociation, oxygen atoms are 1 to 3 lattice sites apart. The applications of STMs are vast and impactful. In material science, they allow for characterization of surfaces, revealing defects, atomic arrangements, and electronic properties. In nanotechnology, STMs are used for manipulating atoms, which was famously demonstrated in IBM's 1989 experiment, where researchers spelled IBM by arranging individual xenon atoms. This opened the door to a new field of atomic scale fabrication. In physics, STMs provide insights into quantum phenomena, and in chemistry, they help study reaction mechanisms at molecular level. However, STMs are not without their limitations. They require extreme stability since even tiny vibrations can disrupt measurements. Additionally, the surface being studied must conduct electricity or be modified to do so, as the tunneling current relies on electrical conductivity. Furthermore, the technique requires expert handling, as positioning the tip with such precision can be challenging. Despite these problems, the STM remains one of the most powerful tools for exploring the microscopic world. It has advanced our understanding of materials and paved the way for innovations in semiconductors, catalysis, and quantum computing. The scanning tunneling microscope is not just an instrument, it is a gateway to the atomic and quantum realm, embodying the perfect blend of physics, engineering, and curiosity driven science. Its invention has fundamentally changed how we see and manipulate the world as its most fundamental level, continuing to inspire breakthroughs in research and technology today. Your applications of quantum mechanics. Quantum mechanics has revolutionized our understanding of the universe, laying the foundation for countless scientific and technological advancements, from enabling precise atomic scale imaging techniques like the STM to powering innovations in the quantum computing, cryptography, and material science. Its applications are reshaping industries and research alike. We unlock solutions to complex challenges, such as developing sustainable energy sources, advancing metal, medical imaging technologies, and enhancing computation capabilities. The journey into the quantum realm is not just a testament to human curiosity, but also a gateway to groundbreaking discoveries that will shape the future.